waiting room. But hello, everyone. Welcome back to the morning session of the Friday of the Student Symposium in Combinatorics. Just a reminder, everyone, please keep yourself muted during the talk unless you have a question for the speaker, in which Hsin Chieh has asked that you're free to unmute yourself and ask, although if you feel uncomfortable doing so, you can address it through the chat and I will get the question answered. But here we have Hsin Chieh Liao from the University of Miami talking about Stembridge codes and permutahedral varieties. Hsin Chieh, take it away.
Okay, yep. Thanks for having me here, giving me an opportunity to talk about my research. So as you can see, like my title, I changed my title a little bit, so it's different from the program book. So today I will talk about Stembridge codes and permutahedral varieties. So yeah. So first, we'll start with the Eulerian polynomial. So it's just a polynomial describe the distribution of descent or exceedance statistic on permutations, and we call the coefficient of this polynomial is what we call the Eulerian numbers. And so Scherzian and Wax, they in 2010 consider the symmetric function Q and JX, whose generating function has this closed form, and the H here is just the generating function of the complete homogeneous symmetric function. And they show that if we take the principal specialization on this Q and XT and doing this, so principal specialization basically just means so your symmetric function have variable x1, x2, x3, and you replace it by 1 q squared. So doing this, you will get it turns out you will get this is some Q analog of the Eulerian polynomial. So this Q and XT is actually, we can view it as some kind of symmetric function analog of the Eulerian polynomial. And it turns out that so these closed form has appeared in some literature before. So yeah, in the context of permutahedral variety, which is a geometric object. And what is this thing? So in general, giving you a polytope P, we can associate a toric variety XP, and we consider P to be the dual permutahedron, which permutahedron is defined as the following. So if we look at the one-line notation of permutations and view it as the coordinates in Rn, and we take the convex code of all the permutations, if it will becomes a polytope, and this polytope is what we call the permutahedron. So when P is the dual permutahedron, so the toric variety will have the following features. So basically, its Betti number, which is the dimension of its cohomology, is equal to the H number of the permutahedron, and which is also the Eulerian number we talked about before. And there's also an SN action on permutahedron, which makes this cohomology as an SN representation. So if we let this CH be the Frobenius characteristic map, which is just a map sending the representation to a symmetric function. So Prochassi and Stanley, they compute the Frobenius characteristic of these toric variety, this cohomology, and it turns out they get the same closed form. Yeah, these closed form. And another place that these closed form appear is in a paper where Stembridge defines something called the codes of a permutation. So we just called it the Stembridge codes. This is totally combinatorially defined objects, and which is defined as the following. So now if that A, this is just an alphabet set. This is a set of non-negative integers, and a code is just something like a sequence like this. So its definition is just it is just a marked sequence alpha over this alphabet set, such that if you have some non-zero j appears in alpha, then any number from 1, 2 to j, it will also occurs in the sequence, and it occurs at least twice. And also for each these non-zero j in the sequence, with a mark is assigned to the ith occurrence of j for some I greater or equal to 2. So like you can see in this example, when 3 occurs in the sequence, so we also have 1 and 2, and both 1, 2, 3, they have at least 2 occurrences in the sequence. And there is a mark assigned to each one, to some 1, 2, and 3. Yeah. And these one, so this mark always appears in the second occurrence or like after the second occurrence. Yeah. And we usually denote a code as a pair like alpha f, where this alpha is just the sequence, and f is just is to record the position of the mark. Yeah. So for example, this f1 equal to 2 means that so we look at the marked 1, and there are 2 1 in front of the marked 1, so f1 equal to 2. And f2 equal to 1 because we look at the mark 2, there are only 1, 2 in front of this mark 2. Yeah, and f3 is so on. So then we can define what is the index of the code, which is just we sum up all these f1, f2, and f3. So in these examples, the index is just 2 plus 1 plus 1, so it's 4. And these are the examples of codes of length 3. So there are 6 of them. And if we look at the distribution of its index, you can kind of see it's 1 and 4 and 1. So it's the same as the Eulerian polynomial. Yeah. And so it turns out there is an ASCII action which preserves the index as the following. So given your permutation sigma, it acts on the codes by just permuting the sequence part of the code and just leave the mark unchanged. Yeah. And so these as an action, it will induce a graded representation of Sn on the space spanned by codes of length n. So in 1992, Stembridge, he computes the Frobenius characteristic of this representation, and it turns out that he obtains the same closed form we saw before. Yeah. So then we can ask the natural question. So why do these two different objects, one is combinatorial, one is geometric, they have the same Frobenius characteristic? Yeah. And to answer this, we will need some theorem. So we need a theorem to view this cohomology as a quotient of a Stanley-Reisner ring. And so now we'll talk about this theorem. So the setting is if we have some polytope P, which is a simplicial lattice n polytope in Rn, and it has its phase span is sigma, and the origin is inside its interior. And this Z delta P basically it's a Stanley-Reisner ring of the boundary of this polytope, where it's just some ring associated to a simplicial complex. Yeah. And 6 sigma I is just some linear form which you record how you put your polytope inside the space. So a theorem of Danilov and Stembridge says that if this phase span carries a proper G action, so G is a group, then we can view the cohomology. So this cohomology of toric variety is isomorphic to the Stanley-Reisner ring of the boundary of the polytope modeled these linear form. And they were isomorphic as a G module. So in our case, we will view, so in our case, this polytope P is just the dual pyramidal. And we will see later that, so we will view the left-hand side of these as Chowian of Boolean matroid later. Yeah. So before talking about Chowian, we need to know, so what is the matroid? And a matroid n of rank R on some grounded set 1 to n. This can be thought of just a set of vectors v1 to vn, and you span an r-dimensional vector space over some field. And the set of flats of this matroid, so Fn, these are just a subset which models the subspace of V. So the set of Fm can be written as the following. So it's just subset of the 1 to n set that is equal to the 1 to n set intersect with some subspace W of V. And we said that the rank of this flat F is just the dimension of this subspace. So this is an example of a matroid of rank 2 on 1 to 4 set, because there are 4 vectors and these 4 vectors span an R2. Yeah. So the set of flats, and this in this case just the empty set, and 1, 2, 4, and 3, and then it will be the 1, 2, 3, 4, which is represent the OR2. So if we consider the inclusion relation with these Fn, it forms a lattice of lattice, and this is the corresponding Hasse diagram of this lattice. So, and what we care about is the Boolean matroid. Well, basically, it's just the set of unlinearly independent vectors, and its flats are just all the subset of the 1 to n set. So, for example, when n equal to 3, this Boolean B3 has grounded set 1 to 3, and all the flats are just all subsets of 1 to 3. So are these things, and the lattice of flats are just the Boolean lattice. So now, because we know what is a matroid, so the Chowian of a matroid is defined as the following. So we denote it as AN, and it is just a polynomial ring model some ideal, and the polynomial ring, its variable is indexed by non-empty flats, and we will model this xf times xg, where fg are incomparable in the lattice of flats, and then we also model these some linear form. Yeah. So basically, just kind of remember that this is just some something in the numerator and model some linear form. So, yeah. And it turns out this AM is a torsion-free Z module. And so there is a related concept of Bergman fan and Bergman complex that is related to the Chow ring. So for some subset S of n set ES is, we denote ES as the sum of all EI, where I run over all the element in S, and EI is just the standard basis vectors. And the Bergman fan of this matroid, so a fan is just like a collection of cones which puts in together in a nice way. And so the Bergman fan of M is just a simplicial fan in the space Rn, modeled these O1 vector, and its rays are spanned by all the EF, where F is non-empty proper flats. And so these rays, EF1 to EFK, they will span a cone in this fan if and only if this F1, this flat F1 to FK, it forms a flag in the lattice of flat. Yeah. And once we have this fan, we can get the Bergman complex by just intersecting it with a sphere. It will get a simplicial complex. And if you observe these kind of definition carefully, you will kind of see that the numerator of the Chow ring, AM, is just the Stanley-Reisner ring of the Bergman complex of M. So yeah, you can see. So this thing is the standardizing ring. So this is an example of B3. So these are the Bergman fan. You can see the rays are those E1, E2, E3, and E2, 3 are all the subset of N set, 1 to N set. And actually E3 and E2, 3 here, they will form a cone here. So this is actually a cone because 3 and 2, 3 is a flag in the flat. That is a flat. And there's also a cone here between E2 and E2, 3 because 2 is contained in 2, 3. So there's always a cone, there's a cone here and cone here. And if you look at these, this is actually the phase fan of dual of permutohedron when n equal to 3. And we can intersect it with a sphere, then we'll get a simplicial complex like this, which is a hexagon. So this is the Bergman complex, and it is the boundary of the permutohedron when n equal to 3. Well, and it is also the boundary of the dual one in this case. So because of these, like from definition of the Chow ring and also the Damnon law of Stembridge's theorem, we know that the Chow ring of Boolean matroid can be, it has these form, so it can be viewed as the cohomology of the toric variety as an, yeah, they have the same as a representation. So once we know these, so there is a theorem by Fechner and Zvinsky. So when they found a basis for the Chow ring, so the Chow ring of AM has these bases, and we just apply these theorems. So apply their basis on when Rm is Bn, then the set of basis elements of this Chow ring of Boolean matroid will consist of the monomials, and they are indexed by flags of subset of n set. And they are exponent like A1, A2, AK here, they will satisfy these conditions. And these are the examples, 2 examples of the basis element. So it will be the monomial like these. And because they are indexed by subset of n set, so there's a natural Sn action on these subsets, and it will induce an Sn representation on this Boolean Chow ring of Boolean matroid, and it is a permutation representation. So so what we did is there is actually a very easy bijection between these monomial bases and the codes of the length n we just we saw, and these bijection actually respect the Sn action on both sets, and it takes the degree to the index. And these are the examples when degree is 2 and n is 4. So you can kind of see, for example, this x1, 4, x1, 2, 3, 4, it maps to these codes. And the way how you biject is, so see, if we start with 1, 4, so we just put 1 in position 1 and 4. And like the next set is 1, 2, 3, 4, so we add 2 and 3, so we just put 2 in position 2 and 3. Yeah. And the degree maps to correspond to index. We can see it from by this example. So we can see x2, 3, 4. So 2, 3, 4. So we put 1 at position 2, 3, 4, and the degree is 2. So this means f of 1 is 2. So here, this is we will put the mark at here. Yeah. So this is, so from this bijection, we kind of see that the code and the monomial bases are kind of like the same thing. Yeah, and so this is why, like, okay, we have a, so we have an the degree J Chow ring of Boolean matroid, and these the space spanned by the codes of length with index J, they are isomorphic permutation representation. Yeah. And so if we look at, to summarize, so what we did is just, we look at all variant polynomials, which this is enumerates permutations. And the object we kind of care about, the combinatorial object, is the code, Stembridge codes and the geometric object corresponding to this is the permutohedron. And we show that these codes and the basis of the cohomology of this toric variety are kind of the same thing. And we do this by view the cohomologous Chow ring of Boolean matroid. Yeah. And so I don't have time to talk about this, but like there is actually some extension on these things. So if we consider instead of Eulerian polynomial, we consider something called binomial Eulerian polynomial, which is introduced considered by Postnikov, Reiner, and Williams. We define as the following. And in this case, we have a parallel story, and everything goes very well. Like just you can translate one concept to another. So like permutations will become like partial permutations or like decorated permutations defined by Postnikov. And Stembridge codes, we kind of define something called extended codes, and permutohedron would become some polytopical stellohedron. And we also show that the basis of this toric variety of stellohedron is kind of the same thing as extended codes by viewing these cohomologies, something called the augmented Chow ring of Boolean matroid. Yeah. And yeah, so these are like a parallel story. Yeah. And I'm still writing the paper. Yeah. And I think that's all I want to say. Yeah. Thank you for listening.
Let's all thank the speaker. Okay, do we have any questions?
So I have a question. So since this is the like this is some action on the cohomology of the toric variety of the permutohedron, those are, I guess, like the thing there that's giving the dimension is permutations with a fixed number of descents. Is there an easy way to understand is there an easy way to go from either codes or the Feshner-Ulanowski basis to permutations, still preserving the SN action?
Preserve SN? Well, there is some bijection. Well, so Stembridge actually has a bijection between codes and permutation, and it will send the index to the to exceedance. And I think that, and if you want like send like index to like descents, I think there is still no result being published, but like I know there's like some others that he probably have like a bijection, but like he didn't write it down. Like Spencer Beckman have some bijection of these things, but he didn't really publish it yet. Yeah. And but none of these I know like they will like there's an SN like preserve some SN action, like, or like we didn't know how to SN act on say permutations. Yeah, we have SN action on the codes, but there's still no easy way to describe how the corresponding SN action act on permutations. Yeah.
Thank you.
I also had a question. Could you go back to page 7 or slide 7?
Yep.
Okay, right. So we have this cohomology ring, and it's defined as the quotient of a Stanley-Reisner ring.
Yeah.
But a Stanley-Reisner ring's already a quotient, right?
Yeah.
So I'm wondering, do we have any understanding of what the ideal is in just the standard polynomial ring that we're quotienting? Because, you know, if you're taking a quotient over quotient, you're just quotienting out by some bigger ideal in your original ring.
Yeah.
Does that ideal have a nice description? Is there anything known about that?
Oh, you mean this ideal? Like
Yeah, it only
Yeah.
in, just in ZX1 instead of Stanley Reasoner ring. Like, what is the image of that ideal when you lift your projection or your quotient?
Oh, you mean like these inside the Stanley Reasoner ring?
Well, not the Stanley Reasoner, because the Stanley Reasoner ring is a quotient of a polynomial ring.
Yeah.
So there's some polynomial ring underneath all of this. What is the image of what is your ideal, theta 1 through theta n in the
These
polynomial
two.
ring?
Yeah.
Yeah.
Yeah. Yeah. I don't know, but like, I don't know why these will be true, but it's kind of like, yeah, as I say, this sigma 1 to theta 1 to theta n, these things is kind of like the core you how you put your polytope inside Rn, like it kind of recording your where your vertex set is, kind of like that. But yeah, but I don't know why when you model these you will get like the cohomology. Yeah.
Okay. No, that's a very fair answer. I also think that is all the time we have for questions. So if we can all thank our speaker again.